My name is Philip Ledent, and I represent the Masonry Institute of Michigan. And today's video is going to focus on the flexural design of masonry lintels. And to do that, we will use our provisions out of our TMS 402-602, our 2016 edition, although not much changed between 2013 and 2016. And we will also point out changes that are coming in our 2022 version of our standards. So today, again, we're going to focus on flexural design of masonry lintels. In future videos, we will look at flexural design of masonry walls, which use the same provisions, and we'll talk about how to do that in, again, some upcoming videos. So today, our codes references we'll use are TMS 402-602, which is our building code requirements and specification for masonry structures. And again, we're using our 2016 version for today's presentation, which is adopted in our 2018 IBC. And again, not much changes between 2013 and 2016. Our 2013 version of our TMS 402-602 is adopted in our 2015 IBC. So depending on where you are practicing, just verify in chapter 35 of your building code, which has referenced standards, which version of the TMS 402-602 is referenced where you're practicing. We will also use design of reinforced masonry structures, which is a great reference published by the Concrete Masonry Association of California and Nevada. And we will use strength design of masonry, which was recently published in 2020 by the Masonry Society. You can see down here in the bottom right. And I use this class for the course I teach at the University of Toledo. And I highly encourage, if you are a practicing engineer, pick up a copy of Strength Design of Masonry. It has a lot of really great examples that really clarify code provisions and a lot of really great designer notes for things that are commonly done and how you can efficiently design with masonry. So today, again, we are going to focus on strength design of masonry, which is covered in chapter 9 of our TMS 402. And so the fundamentals of strength design. So strength design is similar to LRFD, which is our load and resistance factor design. So if you are used to using AISC 360 for steel or ACI 318 for design of reinforced concrete, both of those standards use a similar LRFD or strength design approach. So we essentially take our working loads and we multiply them by a load factor, which is typically going to be larger than 1, and we determine our factored loads. So you'll go to ASCE 7 or the IBC or whatever your loading document is, and there are different load combinations for different factored loads. And so again, we will take our loads, for example, dead or live loads, multiply them by a load factor, which is typically larger than 1, to determine our factored loads. And we'll take those factored loads and determine which factored load combination is going to control for whatever element we're considering. And so that's our load side of our equation. On our resistance side of our equation, due to uncertainty in material strengths, dimensions, approximation or analysis, placement or reinforcement, workmanship, things like that, we take our nominal strength. So again, today we're focusing on flexural design. So we take our nominal flexural capacity or our nominal moment capacity. We multiply it by a strength reduction factor, which is usually denoted by phi in our codes, which is almost always going to be less than 1, and we come out with a factored capacity. And so out of section 9.1.3, again, chapter 9 is our strength design chapter. It says that masonry members shall be proportioned so that the design strength equals or exceeds the required strength. So to determine our design strength, we take that nominal strength, we multiply it by our phi factor, we then get a design strength, and that needs to be greater than our factored load combination. And so, I mean, kind of fundamentals again of strength design. I took this diagram out of the engineering journal and I have the reference for that. But if we look at kind of a normal probability distribution on our resistance side of our equation, so our design strength side of our equation, that, again, that's denoted by R. And if we have our load effect normal distribution here, usually denoted by Q, we want to make sure that our load factor times our load effect is less than our strength reduction factor times our resistance. And theoretically, we would have a failure where these bell curves kind of cross. And so again, it's all probability based with strength design, but essentially we're factoring our loads up, we are factoring our capacity down, and making sure that our capacity exceeds our applied loads. Some additional requirements out of Chapter 9. If we do design our beams or lintels with our strength design, Chapter 9, we do require that they are fully grouted. So Section 9.3.4.2.4 says specifically beams shall be fully grouted if you use strength design. But I did want to note here, this is not a requirement in Chapter 5, which is our structural elements chapter, or in Chapter 8, which is our allowable stress design chapter. So if you design a beam with allowable stress design under our current code provisions, you would be permitted to design a partially grouted beam. And looking ahead to where things are going, again, our 2022 standard is not yet published at the time of this recording, but we do move that requirement out of Chapter 9 into Chapter 5. So it applies to both ASD and strength design. And it will say specifically beams requiring transverse shear reinforcement shall be fully grouted. So if we have to have transverse shear reinforcement or stirrups in our lintels or beams, then we need to fully grout them. But if not, so if we have a large wall height above our opening, for example, partially grouting may be an option. So if we had a wall elevation here, we have maybe a door opening, we need a couple courses grouted with a longitudinal bar above it as our lintel. We could either use this as our wall height, or we could use our overall wall height as that lintel height. And if we did want to design a partially grouted lintel, we'd want to make sure our compression block is contained in a fully grouted section at the top of our wall, which it almost always will be, because we typically will have a bond beam at that location. And then we will just need to calculate our shear resistance for that partially grouted section above our opening. But we could currently, under our provisions, design a partially grouted lintel using our ASD provisions. And in the future, and once our 2022 standard is published and adopted, we could design a partially grouted beam using either strength design or allowable stress design. So that is coming down the pipeline. Other requirements in strength design. So we do limit our axial compressive force. Here in 9.3.4.2.1, we limit it to 5% of our net area multiplied by our F prime M. Additionally, we have limits on our longitudinal reinforcement. We say our variation in longitudinal reinforcing bars in a beam shall not be greater than 1 bar size, and then not more than 2 bar sizes shall be used in a beam. Beyond that, in 9.3.3, again, strength design is more ductility focused. And so we do limit our bar sizes to a number 9 bar maximum, regardless of whether it's a wall, beam, pilaster, column, whatever the element is. Number 9 is the largest bar size we can use under our strength design provisions. If we use ASD, we could theoretically go up to a number 11 bar, but we do have other requirements that limit our bar size here based on our area. So we can't exceed 4% of our cell area for strength design, or a quarter of our least clear dimension. I'll record a future video on how we can calculate these things. But for example, in an 8-inch block wall, we might not even be able to put a number 9 bar in that cell. We would need to calculate our cell area and see what the limitation would be. But in theory, we could go up to a number 9 bar maximum with strength design. And so strength design, all of our design assumptions are conveniently located in one place, which is section 9.3.2. And so this is everything we need to know to develop our stress and strain diagrams and to solve for our flexural capacity. And so we'll draw those out, and I can kind of go through some of these provisions. So it says strain compatibility exists between reinforcement, grout, and masonry. Nominal strength of reinforced masonry cross sections for combined flexure and axial load is based on applicable conditions of equilibrium. And then here's where we're going to draw our strain diagram. It says the maximum usable strain at the extreme masonry compression fiber is 0.00354 for clay masonry and 0.00254 for concrete masonry, and strains and reinforcement in masonry are directly proportional to our distance from our neutral axis. So if we draw a strain diagram here on the left, we are directly proportional to our neutral axis, which is normally denoted by C. So our distance between zero strain and our maximum compression fiber is going to be denoted here by a C. That's where that neutral axis is in this beam, and I'm just drawing this as an example. Our maximum strain in our masonry is 0.0025 for concrete masonry, 0.0035 for clay masonry, and then we'll have our strain in our steel down here. And we'll talk about that throughout today's presentation because we do have limitations on maximum reinforcement in our strength design provisions. So that would be our strain diagram. And in terms of our stress diagram, we have this relationship here. So it says masonry stress of 0.80 times F prime M is uniformly distributed over an equivalent compression stress block. And so we would have a uniform stress here equal to 0.80 times F prime M. Pardon my writing. We have a B dimension into the page, which would be equal to the width of our beam. So if we have an 8-inch wall and we are constructing a cast in place lintel, our width would be 7.625 inches. And then we have our depth of our stress block, which is normally denoted by A. And A in this case is equal to 0.80 times C, which is the depth to our neutral axis. And I wanted to point out here in ACI 318, that 0.80 is not a constant. It is based on the compressive strength of our concrete and a factor called beta 1. But in masonry, it's taken as a constant, which is 0.80 times C. So A, the depth of our stress block equals 0.80 times C, which is the depth to our neutral axis. So we have everything on the compression side. On the tension side, we have our tension equals our area of steel times our yield stress F sub Y. And our yield stress, because we're commonly using grade 60 steel, is going to be 60,000 PSI or 60 KSI. And so this is how we construct our stress and strain diagrams as we look at masonry beams and lintels. Additionally, there is a note here: masonry and tension does not contribute to axial and flexural strengths. That is for reinforced masonry. If we were designing unreinforced masonry, then we would neglect our tension resistance of our steel and only rely on the masonry. But in reinforced masonry, we neglect any contribution from our masonry and rely solely on the reinforcement. So that's in there as well. And so based on equilibrium, which again is in section 9.3.2, we can develop or determine our nominal moment capacity by setting our compressive force in our masonry equal to the tension force, and that should say in our reinforcement, not in our masonry. So if we have that stress block, again, we have a uniform stress distribution of 0.80 times F prime M. So 0.8 F prime M. We know this dimension is A, and we know we go B dimension into the page, which again is the width of our wall or the width of our beam. We have our reinforcement in the bottom of our beam, so our tension force equals our area of steel times F sub Y, which is again our yield stress. And we know that reinforcement is located at an effective depth from our extreme compression fiber to the centroid of that reinforcement, which is commonly denoted as D. And so by setting these forces equal, we can then determine our nominal moment capacity. So our compressive force will act at the centroid because this is a rectangular cross section. So if we denote that as C, the distance, our internal moment arm here, will be our effective depth minus A divided by 2. And again, we're taking that effective depth from our extreme compression fiber to the centroid of our reinforcement, and we subtract A divided by 2 because our compression force will act at the centroid of our rectangular compression stress block. So A divided by 2 will be the location of that centroid. So now we have everything we need to know to be able to determine our nominal moment capacity. To do that, first, let's solve for A in terms of everything we already know. So if our compression force C equals 0.8 times F prime M, which again is that uniform width of our compressive stress block, times A, the depth of our stress block, times B, the width of our beam into the page in this case. And we set that equal to our tension force, which is equal to our area of steel times our yield stress, F sub y. And if we rearrange this in terms of getting A on one side of the equation, we would divide the other side of the equation by 0.8 times F prime M times B. So A in this case equals our tension force AS times Fy over 0.80 times F prime M times B. And so we can solve directly for the depth of our compressive stress block using our area of steel times our yield stress divided by 0.8 times F prime M times B. And so that would be the depth of our stress block. If we want to know what our moment capacity is, we can quickly solve for that. So our nominal moment capacity, M sub N, would be our tension force or our compressive force, whichever you prefer. Tension force would be our area of steel times our yield stress times our internal moment arm. So D minus A divided by 2. And so we could solve directly for our nominal moment capacity using these variables. If we wanted to rewrite it in terms of the A that we just solved for, we would take our nominal moment capacity equals our area of steel times F sub Y, and we multiply that by D minus, and if we pull the 1/2 out to the front, and then we just have A here. So AS Fy over 0.8 F prime M times B. And so that would be our nominal moment capacity in terms of our area of steel, our yield stress, our effective depth, F prime M and B. So pretty easy, pretty direct for us to solve for our nominal moment capacity if we know the dimensions of our masonry beam and we know our reinforcement. A question though that always comes up, so what is our effective depth of our masonry lintel, which is a really good question. And so to do that, or to determine that, let's look at our different lintel types. So we do have something called the closed bottom lintel units. And typically these are going to come in 8-inch block or 12-inch block occasionally. But to physically manufacture this unit, again, it has a closed bottom here, which is nice because then we can just grout it solid and we don't have to worry about shoring the bottom of it. The manufacturer is going to need to thicken up the bottom of that unit because there's no crosswebs in it. And so when they pull the unit from the mold, it has a tendency to crack through here. And so we obviously don't want our units cracking during manufacturing. And so the manufacturers are going to thicken the bottom of that unit. And so every manufacturer has different molds. So if you are specifying a closed bottom or a U-shaped type unit like this, make sure to check with your local manufacturer. But usually the lowest we can get reinforcement in a U-shaped lintel like this is going to be maybe 3 inches from the bottom of our unit to the centroid of that reinforcement. And these closed shape units, again, only typically come in gray standard type units, because if we need to split the unit for like a split face architectural unit or a burnished unit, usually the manufacturing process is going to be too hard for us to actually make a closed bottom lintel unit. So the other way that we make lintels is using a bond beam unit. So it's going to look like a standard unit. And when they make that unit, they are going to put these notches in it so that a mason in the field can take a hammer and knock out the crosswebs. So then we can put our longitudinal reinforcements in here. And so usually with a knockout type bond beam unit, the lowest we can get the reinforcement in that unit is going to be at about our height of our unit divided by 2. And so if we're using a split face type unit, burnished unit, typically the lowest we're going to be able to get those longitudinal bars will be the height of that unit divided by 2. And we can orient those either this way, right side up, or we can orient them upside down, which is done on occasion. So they'll knock out that crossweb again in our units. We'll put those longitudinal bars in here. And we could then use either like chairs to support these longitudinal bars. And we'd have some type of plywood or OSB down here so that when we grout this solid, we are keeping the grout confined to our lintel. So we could do that with chairs. We could also, if we had the unit oriented upside down, again, they're going to knock those webs out. We have the reinforcement here. We could use wire ties and wire the reinforcement to this bed joint above it. And again, then shore the bottom here and grout this solid. With the first way, right side up, we can actually put those reinforcing bars directly on the crosswebs. The TMS 602 does allow that for support of our reinforcing bars. And then again, we're going to grout this in here. But since the bottom here is open, we will have to somehow cover that to make sure that our grout stays confined to our lintel units. And then again, our opening here, our door or window, whatever, will be located beneath that. And so usually we're not going to see this grouted core beneath it, depending on where that window or door frame is located. But again, if we're using a split face or burnished unit, typically the lowest we'll be able to get our reinforcement is about that unit height divided by 2. If we have a closed bottom or U-shaped unit, typically we can get the rebar, the centroid of the rebar, 3 inches from the bottom of our unit based on the manufacturers that I worked with and got their mold drawings for. And so using what we learned, we can now look at an actual problem and determine our nominal moment capacity. So here we have a 3-course lintel. Let's say it's a split face wall. So maybe we have a single width exterior wall, maybe a warehouse, something like that. So we have split face units. So we know we can't use a U-shaped lintel. So we will use a knockout unit, which means again, that rebar is going to be located at h/2, so 4 inches from the bottom of that unit. And so our effective depth D would be our lintel height, 24 inches minus 4 inches, so 20 inches. And so we'd have that here. So we have 24-inch deep lintel, 8-inch block. We are reinforced with 1 number 5 bar. So the area of a number 5 bar is 0.31 inches. And so again, using what we already learned, so our nominal moment capacity is going to equal our area of steel times our yield stress multiplied by D, our effective depth, minus 1/2 times ASFY over 0.8 F prime M times B. And in this case, we know all of those variables. So our nominal moment capacity and is 0.31 inches squared. Our area of a number 5 bar, 60,000 PSI. Our yield stress for grade 60. We have D 20 inches minus 1/2 of our area of steel, 0.31 inches squared times 60,000 PSI over 0.8 times F prime M, which would be 2,000 PSI, our minimum, times B, 7 5/8 of an inch, so 7.625 inches. Sorry, I had to cram that in there. So if we multiply this out, our nominal moment capacity for this 3-course lintel with 1 number 5 bars, 357,820 inch pounds. And so if we convert that into foot kips, we're looking at about 29.8 foot kips. And our phi times our MN, so our phi for reinforced masonry in flexure is 0.90. So if we take 0.90 times 29.8 foot kips, that comes out equal to 26.8 foot kips. So our factored moment capacity would be 26.8 foot kips. So that would be our design moment strength. Our nominal moment strength is 29.8 foot kips. And again, this is very direct and easy for us to solve for our nominal capacity. If we know the geometry of our beam, in this case, it's a 3-course lintel, it's an 8-inch wall, and we know our reinforcement, in this case, a number 5 bar that's grade 60. So hopefully that makes sense. Pretty straightforward, calculating out nominal moment strength. In terms of what affects our moment strength, so F prime M has been brought up a couple times. And so I plugged in some numbers for that specific beam. And if we increase our F prime M from 2,000 to 4,000 PSI, which would be, double the F prime M, so 100% increase, it actually only affects our moment capacity by 2%. And so F prime M does not have a significant effect on our factored moment capacity or our flexural strength. It does have a big impact on things like our bearing strength, axial capacity, maximum reinforcement, development length. So F prime M is very important, but in terms of flexural capacity, not so much of an impact. And so 2,000 PSI is where we are as far as a minimum F prime M. Our ASTM C90 which is our ASTM for load-bearing concrete masonry units, currently requires 2,000 PSI minimum unit strength. And with a 2,000 PSI minimum unit strength, that gets us a 2,000 PSI F prime M. So this is a good minimum place to start. If you need a higher value of F prime M for, again, shear, axial load, things like that, axial capacity, sorry, check with your local producers. Some of our producers in Michigan, especially if we're looking at architectural units, which are pretty dense, just to survive production, we can get some pretty high breaks on our units. So if you need something higher, ask your local producer and see what the cost impact would be for that. But F prime M, again, not a huge impact on our factored moment capacity. In terms of, again, what affects our moment strength, if we increase our bar size, so if I go from 1 number 5 to 2 number 5s, again, that's a 100% increase. We get a 92% increase in moment capacity. If we go to 1 number 6, it's about a 40% increase. 2 number 6s, you can see it's about 163% increase in moment strength. And so we actually have kind of a directly proportional relationship here. So however percentage wise increase we make in our reinforcement, we can kind of expect the same percentage increase in our flexural capacity, which is kind of interesting and makes sense just because of the equations. But that's a good thing to remember. F prime M is not going to have a huge impact on flexural capacity. However, our area of steel, we have kind of a directly proportional relationship between area of reinforcement and our moment capacity. So moving on, we also have requirements on minimum reinforcement requirements, and those are in sections 9.3.4.2.2.2 and 9.3.4.2.2.3. And these restrictions are there, if you read the commentary in the TMS 402, they're there to prevent brittle type failures. If we have a situation, which could occur maybe, where a beam is very, very lightly reinforced, that the bending moment required to cause yielding of the reinforcement is less than the bending requirement that is going to cause cracking, we can actually have a very brittle type failure. And so our nominal moment capacity needs to be greater than or equal to 1.3 times our cracking moment. And I'll show you how to calculate that here in a minute. Or our area of steel needs to be greater than 4/3 times our area of steel required by analysis. And so again, those are here in these two sections of our code, and I'll kind of go through these in a few examples here in a minute. But those are our minimum reinforcement requirements. And to calculate our nominal cracking moment, M sub CR, we're going to do that exactly the same as we would for a reinforced concrete member, which most people are familiar with. So we have our modulus of rupture F sub R, and that's going to equal My over I, which if we took statics or mechanics of materials in college, that equation should be very familiar. So if we rearrange that in terms of our cracking moments, our cracking moment equals our modulus of rupture times I, our moment of inertia, divided by Y, our distance between our neutral axis and our extreme fiber. And because we are a rectangular cross section with masonry, we can pretty easily solve for Y and for I. Our I is BH cubed divided by 12, and Y is going to be H divided by 2. And so plugging those in, we get our cracking moment is going to equal our modulus of rupture F sub R times B, the width of our beam, times H, the height of our beam, squared divided by 6. So pretty easy for us to solve for our cracking moment. Our modulus of rupture comes out of table 9.1.9.2 of our TMS 402. And it's based on a few things that I note here. So the direction of our flexural tension stress, whether we are parallel or normal to our bed joint, our unit type, whether we are solid or hollow, or we can calculate it for partial grouting as well. Grouting, fully grouted versus ungrouted, type of cement, S or M, and bond type, running bond or not running bond. And so for lintels, our direction of our flexural tension stress is going to be parallel to our bed joints. So if we draw out a lintel here, I'm an engineer, not an artist, but we have a lintel here. We have load being applied to it. That load is going to cause this lintel to bend, and behave in flexure. And so our tension stress is going to be in this direction. So parallel with our bed joints, and our compressive stress is going to be acting this way, which should be, again, parallel to our bed joints. If we had a wall and we had wind load applied to it, let's say it's an exterior wall, that's going to create stress in this direction, tension and compression stress, which again then is going to be perpendicular to our bed joints. And as you will see in this table, our modulus of rupture is much greater parallel to our bed joints than it is perpendicular or normal to our bed joints. But again, this is table 9.1.9.2 that we use for determining our modulus of rupture. So if we wanted to figure out our modulus of rupture and our cracking moment for the beam shown below, 3-course lintel, our depth is 20 inches, and we're using type S masonry cement mortar and fully grouted hollow units. We can do that pretty quickly and easily. So usually type S is what we are using for our structural or load-bearing type walls. In Michigan, we use a lot of masonry cement mortars because we are not in a seismic state where we have a lot of seismic restrictions, and most of our contractors are used to using masonry cement mortars. I advocate for using masonry cement mortars, especially in veneers in Michigan, because they're easier to clean. But we can get into that topic a whole nother time. So we have everything we need to know here. So again, our cracking moment is going to equal our modulus of rupture, F sub R, times our B, our width, times our H squared divided by 6. And we know our B is 7 5/8 of an inch, so 7.625 inches. We know our H in this case is equal to 2 foot or 24 inches. We know our modulus of rupture is 160 psi from our previous slide. So if we go to type S, masonry cement mortar, so that would be this column here, we are parallel to our bed joints and we have fully grouted hollow units. That means we are here 160 psi. So that's where that comes from. And so plugging all those values in, we get our cracking moment equals 160 psi times 7.625 inches times 24 inches squared divided by 6. And our cracking moment in this case, I'll write it up here, is going to equal 117,120 inch pounds. And if we divide that by 12, we get 9,760 foot-pounds. So pretty straightforward to calculate our cracking moments for a beam, as long as we know the type of mortar used, so we can determine our modulus of rupture and the geometry of our beam. A good relationship, and they discuss this in the Strength Design of Masonry book that I recommended, is if we calculate our applied moment, M sub U, so our factored moment, if we are greater than or equal to 117% of our cracking moment, then we meet the minimum requirements for reinforcement of our beam. And I'll show you how they develop that relationship here. So phi times Mn needs to be greater than M sub U. And so again, our factored moment capacity needs to be greater than or equal to our factored moments. And so rewriting this, we get M sub N is greater than or equal to M sub U, our factored moment, divided by phi. And phi, again, is 0.90 for members in flexure. And so M sub N is then greater than or equal to 1.111 times M sub U. And so rewriting that in terms of our M sub N needs to be greater than 1.3 times our cracking moment, our minimum requirements. We have 1.111 times M sub U, our applied factored moment needs to be greater than or equal to 1.3 times our cracking moments, and then just moving all of our numbers over to one side, we get M sub U greater than or equal to 1.3 divided by 1.111 cracking. And so as long as our applied moment is greater than or equal to 1.17, times our cracking moments, we have satisfied our minimum reinforcement requirements for our beam. So just a nice little relationship. I mean, typically we'll have to solve for our cracking moment anyways for deflections, and we obviously have to solve for our ultimate moment for designing our beam. So a pretty easy way for us to check that we meet those minimum requirements. In addition to our minimum reinforcement requirements, we also have maximum reinforcement requirements, which are in section 9.3.3.2. And our maximum reinforcement requirements are really there to promote ductile behavior. But I did want to note here that we are completely changing those requirements in our 2022 version of our TMS 402. Again, this has not been published yet, but I believe these requirements will indeed be in there. And it makes it very similar to ACI 318, which, if you know how to design concrete beams, is good. And so we'll go through what they are now, and at the end of today's presentation, I'll show you what they're going to be. And so here they are, 9.3.3.2 on the right-hand side. Strain gradient shall be assumed corresponding to a strain at the extreme tensile reinforcement equal to 1.5 multiplied by the yield strain and a maximum strain in the masonry as given by section 9.3.2. And so again, that 1.5 factor is going to apply to CMU lintels, walls loaded out of plane, and intermediate and special reinforcement masonry shear walls dependent on our MU divided by VU DV ratio. And so we'll talk about this, but essentially in this diagrams from the design of reinforced masonry structures, this is what we are trying to do to ensure that we have ductile behavior. So our acceptable strain profiles, we are greater than 1.5 times our yield strain. If we do not have a strain at least 1.5 times our yield strain, then that would be unacceptable because it would not behave ductily. And our yield strain for grade 60 reinforcement, according to Hooke's law, so if we had our yield strain equals our yield stress divided by our modulus of elasticity of steel, so we'd have 60,000 psi divided by our modulus of elasticity, 29 million psi, and that's going to come out to our yield strain of 0.00207. And so we want to make sure that our reinforcement strain is 1.5 times that yield strain or greater to ensure that we have yielding of our reinforcement before we have crushing of our masonry, because we want to avoid brittle type failures. We want to promote ductile behavior in our masonry wall systems. So that's why those maximum reinforcement ratios are here. And so in our commentary out of our TMS 402, it provides this equation for fully grouted members with only concentrated tension reinforcements. And so we know what most of these values are. So our F prime M, again, is going to be 2000 PSI minimum. Our strain in our masonry is 0.0025 for concrete masonry, 0.0035 for clay masonry. So we know what those are. Again, our strain in our steel is going to be 0.00207. Alpha in this case is 1.5 out of the section 9.3.3.2. And our yield stress here is going to almost always be 60,000 PSI. And so if we wanted to rewrite it in terms of stresses and our modulus of elasticity, again, we can do that pretty straightforward here. So 2000 PSI, we know 0.0025 for concrete masonry. Again, our yield stress 60 KSI or 60,000 PSI, modulus of elasticity 29,000 KSI or 29 million PSI. And again, our yield stress here is usually going to be 60 KSI. So pretty easy for us to solve for this rho max or maximum reinforcement ratio. And I've calculated it for you below here. So for grade 60 reinforcement, which is what we will commonly be using, I've calculated it for various values of F prime M. So this is a range here from 2000 to 4000 PSI. And again, I mean, earlier I showed you F prime M does not have a huge impact on flexural strength or moment capacity, but it does have a very significant impact on our maximum reinforcement ratio, as you can see here. So for 2000 PSI, which would be our minimum that we're going to use in design, 0.00952 would be our maximum reinforcement ratio. And again, our rho is typically going to be our area of steel divided by B times D is what that reinforcement ratio is. If we had a structural clay unit with an F prime M of 3000 PSI, the maximum reinforcement ratio would be 0.01697. And so I have a table on the next page with what this kind of equates to. So if we wanted to know in terms of reinforcement, what this looks like, and this would assume a closed bottom lintel unit or a U-shaped unit. So like you can see at the top here, and again, the lowest we can get that reinforcement usually is 3 inches from our centroid of our reinforcement to the bottom of that unit. So I took our D minus 3 inches for these calculations below. So if we had 2000 PSI, we had an 8-inch wall or an 8-inch wide unit. And if we had a 1 course bond beam, so our effective depth D is 5 inches, we can technically only fit 1 number 5 bar in it because our maximum reinforcement area would be 0.36 inches squared. The area of a number 5 bar is 0.31 inches squared. And so obviously we can only fit 1 number 5 bar in there. We can't even fit 1 number 6 bar in there without exceeding our maximum reinforcement ratio. If we increased our F prime M to 2500, we could fit a number 6 bar in there because the area of a number 6 bar is 0.44 inches squared. But I tabulated all these out. So if you wanted a very quick reference for what reinforcement would satisfy the maximum reinforcement requirements, you could use this table. This is something I'm working with our contractors on in Michigan because commonly they are putting 2 number 5 bars in our lintels or bond beams. Which is fine, but with our maximum reinforcement requirements, we would technically exceed our maximum allowed amount of reinforcement with a 2000 PSI F prime M. So again, this table is available. If you're interested in it, send me an email and I can give it to you. But this is just our maximum reinforcement area in terms of our rho max or maximum reinforcement ratio. In terms of designing lintels, so we do have an approach that they go through in strength design of masonry, which is what I typically use for designing lintels. So first we determine our material properties. Typically we're going to use grade 60 reinforcement. If you want to specify something other than grade 60 reinforcement, make sure it's very, 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 very clear in the contract documents. I ran into a condition on a project where they needed it was a different yield stress and it was weldable reinforcement and it wasn't very clear in the diagrams and it turned into a whole issue. So grade 60 is industry standard. So if you want to specify something other than that, make sure it's very clear as to why and what you're specifying. And the minimum F prime M that we're going to use is 2000 PSI. If you want to use something greater than that, again, make sure it's very clear in the contract documents. Contact your local producers, get some block test reports and make sure they actually make what it is you're specifying. In terms of lintel depth, at the MIM, we very, very much encourage designers to specify a depth that you do not need shear stirrups. And I will cover that when we record another video on how to calculate shear capacity. But stirrups are very, very difficult to use in actually physically constructing them. And so if we don't need them, don't use them. If we just need to add another course or two fully grouted to increase our beam depth as such that we don't need stirrups, it's much more cost effective than adding stirrups. And so again, I'll cover that in another video, but we'll determine our lintel depth. And again, we're going to determine that such that we don't need stirrups. Then step 3, we will determine the depth of our compressive stress block. And again, this procedure is out of strength design of masonry. We'll solve for our required amount of reinforcement, AS required, check our minimum values, make sure we have enough reinforcement in our beam to satisfy those code requirements that we need our nominal moment capacity to be greater than or equal to 1.3 times our cracking moments, or the area of steel to be greater than 4/3 of what is required by analysis, and then verify rho max, our maximum reinforcement equation. So don't want too little reinforcement, don't want too much reinforcement. We want just the reinforcement that satisfies our code provisions. Again, if we are using U-shaped lintel units, make sure the reinforcement fits in the lintel. I've gone through a lot of mold drawings and things, and so if you have a question, reach out. I'm happy to go through it with you. But there's a lot of requirements in terms of grout space, requirements, whether we're using fine grout or coarse grout, our clear cover requirements if we're exposed to earth or weather, fire rating requirements on where that reinforcement needs to be, clear distance requirements. So no matter what, we want to make sure that reinforcement is actually fitting in whatever it is we're designing. And if you have questions about that, again, I'm happy to help with that. So if we wanted to design a lintel section, so we'll take everything we've learned up to now in this video, and we will apply it to this lintel here. So we have a dead load moment of 150 inch kips. We have a live load moment of 150 inch kips. F prime M is 2000 PSI. We'll be using type S masonry cement mortar, and we have a yield stress of 60,000 PSI. Our lintel depth, we have a 3-course lintel, so we are 24 inches. Our D value here is 20 inches. Our B value for an 8-inch block wall will be 7 5/8 of an inch, or 7.625 inches. We have one longitudinal bar, so whatever we solve for, we need one bar that satisfies that. And so we'll go through and solve this. So the first step, again, is to identify our geometry here. So we know our D, our effective depth, is 20 inches. We know our F prime M is 2000 PSI. We know our H is 24 inches, our height of our beam, and we know our yield stress, F sub Y, is 60,000 PSI. So again, that's step one, just identify our known values. Step two, we'll solve for our factored moment capacity. So again, we take our applied loads and we factor them up. And the controlling case for this particular lintel, if we use a load combination, would be 1.2 dead plus 1.6 live. We would have to check all of the different load combinations, but by inspection, 1.2 dead plus 1.6 live controls for this moment, this lintel, I'm sorry. So 1.2 times 150 inch kips dead plus 1.6 times 150 inch kips live. And so our applied moment, our design moment, M sub U, is 420 inch kips. If we multiply that by 1,000, we get 420,000 inch pounds. So we know all of our parameters, we know our design moment, so now we can solve for the required reinforcement. So step three, we solve for the depth of our stress block. So A equals D minus the square root of D squared minus 2 times our M sub U, our design moment, over 0.8 times phi times F prime M times B. And that equation is from a couple of slides ago. So A equals 20 inches minus the square root of 20 inches squared minus 2 times 420,000 inch pounds divided by 0.8 times 0.9, our phi factor, times 2000 PSI, our F prime M, times 7.625 inches, our B, our width of our lintel. And so A comes out to 2.01 inches. And so that stress block at the top of our beam is 2.01 inches deep. That's what that's telling us. All right, now that we have A, we can solve for our required area of steel. So our required area of steel, step 4, A sub S required equals 0.8 times F prime M times B times A divided by our yield stress Fy. So we have 0.8 times 2000 PSI, our F prime M times 7.625 inches, our B times 2.01 inches, the A that we just calculated, divided by 60,000 PSI. And so if we plug all that in, our required area of steel comes out to 0.409 inches squared. And so we could use one number 6 bar, which again has an area of 0.44 inches squared to satisfy the requirements. Now we will check our minimum and maximum requirements. So MU needs to be greater than or equal to 1.17 times our cracking moments. Our cracking moment we had solved earlier, but we can do it again just for example's sake. So we had 160 PSI, our modulus of rupture for type S masonry cement, hollow units grouted solid, and the stress is parallel to our bed joints, times B 7.625 inches times H 24 inches squared divided by 6. So our cracking moment was 117,120 inch pounds. So if we take 1.17 times 117,120 inch pounds, we come out to 137,030 inch pounds. And our design moment we were using for this particular problem was 420,000 inch pounds. And so we are much greater than what the minimum required was, 137,030. And so we know we have satisfied the minimum reinforcing requirements. Next, we will look at the maximum reinforcement requirements. So rho in our case is again AS divided by BD. So 0.44 inches squared divided by 7.625 inches times our depth 20 inches. So our rho, our actual rho comes out to 0.0026. And I gave you that table a few slides ago, but for 2000 PSI, our rho max is 0.00952. And so obviously our rho max is much greater than the actual rho we provided. So we do not have too much reinforcement in our beam. So rho max is much greater than the actual rho that we have. So we don't have too little reinforcement. We don't have too much reinforcement. We meet our flexural design requirements. And so for this particular problem with a 3-course lintel and those applied loads, we can make it work with one number 6 bar. I do have some additional notes here, just a couple closing slides. So other requirements relating to beams can be found in chapter 5. So for general beam design, it says span length shall be in accordance with one of the following. Span length of beams not built integrally with supports shall be taken as the clear span plus the depth of the beam, but need not exceed the distance between centers of supports. And it says for determination of moments and beams that are continuous over supports, span length shall be taken as the distance between centers of supports. So it's important to note here that the TMS 402 is silent on the span length for beams built integrally with supports. And so typically with control joints, now we recommend moving control joints off of our openings. That allows us to continue our jam reinforcement up through our lintels and kind of picture frame those openings. But if we do that, the TMS 402 is silent on that. I'd say a reasonable approximation is to use the clear span for beams built integrally with supports, and that's consistent with TMS and strength design of masonry. So typically a bearing length of 8 inches used for supports. And because our jams are typically reinforced with knockout bond beam units, this means that sometimes using a D of 4 inches from the bottom of our unit or of our lintel can be more accurate. So again, if we're using knockout units or bond beam units, we're 4 inches from the bottom of those units. So that's in here as far as our general beam design span length. Span lengths not built integrally with supports would be if we had control joints on both sides. So we are not integral with supports. If we are integral with supports, typically we can use it as maybe our clear span, and be a little bit conservative. If we have continuous, then it would be taken as the distance between centers of supports as well. Additionally, bearing length Like I just discussed, we have a minimum bearing length of 4 inches. Typically, it's going to be 8 inches at our supports. In most cases, in terms of deflections, if we are supporting unreinforced masonry, because we're specifying sections 8.2, 9.2, and 11.2, this is L over 600. But again, this is for unreinforced masonry. So things like a brick veneer, if we're not reinforced horizontally with our masonry, then L over 600 would apply. But that's for unfactored dead plus live. Deflections is a whole nother issue we'll get into in a different video, but that's where these requirements are in chapter 5. Lateral support, so if we had a very tall beam, our compression face of our beam needs to be laterally supported at either 32 times B or 120 times B squared over D. So depending on the height of our beam, that if we had, an 8-inch wall, so 32 times 7.625, we'd be looking at 20 foot 4 inches, for a 12-inch block wall, 11.625, we'd be looking at 31 feet. And so it doesn't apply all the time, but if we do have a really wide opening, we do want to check this and make sure we are supporting the compression face of our beam at the smaller of these spacings. So that's in there. But those are out of chapter 5 again, in terms of span length is in here, deflections are in here, bearing length is in here, minimum of 4 inches, but usually it's going to be 8 inches anyways, and lateral support of that compression face. In the 2022 version of our TMS 402, again, this is not published, and so it will be coming, but once it goes to publication, we can see this in there, and this will be in our 2024 IBC. Very, very similar to the requirements out of ACI 318, where we require in our new chapter 9, the cross-sectional area of flexural tension reinforcement shall not exceed the area required for the beam to be tension controlled. So if we are tension controlled here, we get a phi factor of 0.90, and our net tension strain is going to be 0.003 plus our yield strain. And so again, for grade 60 reinforcement, our yield strain would be 60,000 PSI divided by 29 million PSI, or 0.00207. And so our tension strain needs to be greater than or equal to 0.003 plus 0.002. So our net tension strain needs to be greater than or equal to 0.005, will be what it will be in our new version of TMS 402. So again, as we look at that strain diagram, we get our maximum strain in our concrete masonry, 0.0025 for concrete masonry, 0.0035 for clay masonry. And down here, our tension strain needs to be greater than or equal to 0.005. And so that's what the maximum reinforcement requirements will be replaced with in our new version of our code in 2022, but that's, a little ways down the line here. Currently it's that rho max equation, but in the future, we just need to make sure that our tension strain is greater than or equal to 0.005. And lastly, I did put a table on our website just for help with contractors. So I looked at just a standard load of 1,500 pounds per foot factored load, and what reinforcement we would need, and what maximum spans we could go with different depths of lintels. So again, because of rho max with a 2000 PSI F prime M, we cannot fit 2 number 5 bars in a lintel. But if we had a 2-course lintel, so a height of 16 inches with 1 number 5 bar and 1,500 pounds per foot applied load, we could reasonably go 7'4" with 1 number 5 bar, 11'4" with 2 number 5 bars. 4 courses, we could go 18 foot with 2 number 5 bars. But I'm trying to develop more design aids to put on our website to hopefully make things easier. Hopefully this video helped with your understanding of our flexural design provisions in our TMS 402. If you do have any questions, reach out. I'm happy to either answer them, or if I don't know the answer, I can definitely find someone who does. But thanks for listening, and hopefully you learned something here today.